When a load resistance RL is connected to the power supply, a voltage drop of VL equal to 4 volts is measured across the load. The value of RL over RS is. Since this is a numerical answer type problem, we will round off our answer to the nearest integer. Before we try to solve the problem, let's visit some relevant concepts. On the left, we have an ideal voltage source with zero internal resistance. On the right, however, we have a practical voltage source with some finite non-zero internal resistance. Now let's assume that we connect a load RL to both of our voltage sources, and let's also assume that a current I starts to flow in these circuits. Using Kirchhoff's voltage law, we can write that V out equal to Vs minus I times Rs. Now, since non-ideal voltage source has some finite source resistance Rs, voltage provided to the load, note that the voltage provided to the load is V out. In case of practical voltage source, since Rs is a non-zero number, V out will always be smaller than Vs, which is not the case in case of an ideal voltage source, since Rs equal to 0, and if we put Rs equal to 0, V out will come equal to Vs. In other words, it can be said that in case of a practical voltage source, some voltage is dropped inside the voltage source itself. Extending the same principle to current sources. On the left, we have an ideal current source. On the right, a practical current source. An ideal current source has infinite shunt resistance. A practical current source has non-zero, non-infinite shunt resistance. Again, we'll assume that we are connecting a load RL across our current sources. In case of ideal current source, and current IS will flow through our load resistors. However, in case of a practical current source, some current I will flow in the internal shunt resistance, and the load resistor will only see a current of IS minus I. Note that I have applied Kirchhoff's current law at the highlighted node. Here we can say that in case of a practical current source, some current Is is dropped inside the practical current source itself rather than being delivered to the load resistor. Let's come back to our problem which we were trying to solve. Inside the purple box, we have a practical voltage source with open load voltage as Vs of values 5 volts and an internal resistance Rs. When we applied a load RL, we were given that we read a voltage of 4 volts across the load. We were required to find the ratio of RL over Rs. As a step 1, let's apply Kirchhoff's voltage law in the loop given, and we'll assume that a current I is flowing throughout the loop. Writing KVL, I can say that Vs minus IRS minus IRL equal to 0. Rearranging, I can say that Vs equal to IRS plus IRL, or Vs equal to I times Rs plus RL. From here, we can obtain the value of current flowing through the loop I equal to Vs over Rs plus RL. Now, as a second step, we'll apply Ohm's law across the load resistor. We can write voltage measured across the load resistor VL equal to current flowing through the load resistor, which is nothing but I, times the resistance value, which is RL. Now we'll put the expression of current that we obtained earlier in this expression. So we'll write VL equal to Vs over Rs plus RL multiplied by RL. Taking all the resistance terms to the left hand side, I can write Rs plus RL over RL equal to Vs over VL. Since we already know the value of Vs and VL, we can plug in those values, and I can write Rs plus RL over RL equal to 5 by 4. Simplifying further, I'll simply divide the LHS by RL. So I'll write Rs over RL plus 1 equal to 5 by 4. Or we can obtain the value of Rs over RL as 5 by 4 minus 1, which is equal to 1 by 4. Now, we were required to find the value of RL over Rs, but we have found the value of Rs over RL. We can simply invert the result and can arrive that RL over Rs is equal to 4, which is the value which we needed to find, and we can simply plug in this value in our answer here. Thank you for listening.